Okay, and as they, exchange their energy, they move on, and that's how you can transfer the energy. We'll consider the variations sinusoidal. Okay, of course, the variation can be non-sinusoidal, but you can split into sinusoidal Fourier components. Okay. Okay, we already discussed that, and you see that. Say I think I already discussed it. Say when we have the experience that these fields can penetrate, like the magnet, when you put it somewhere and you have an obstacle on the other side of the obstacle, you find the effect of the magnet, so the magnetic field can penetrate. We have the experience. Also we have the experience probably that the fields can exist anywhere. Like if you put you, um, your magnet inside, if it is submerged in the water, your magnet is submerged in the water, you should still feel the magnetism, right? If you bring another piece of iron under the water, there will be attraction, right? So the magnetic fields or electric fields exist in any medium. And also if there is no medium, okay, if you take it to the space, do you hear me, guys? Okay.
Yes, sir.
If you take a piece of magnet to the space and then bring a piece of iron close to that, what will happen? Will it attract?
Yes, obviously.
Yeah, obviously. So
Yes.
actually the fields can exist in any medium, and even without medium it can exist. It's surprising, but that's the reality. Okay. So this is why the electromagnetic field, electromagnetic wave can propagate through any medium. In general, through any medium, and also uh, without any medium. And that's why we have light here in the earth. Okay. You know that in the past, people had an idea that the whole space is filled in with something which they called ether, because otherwise how come something comes from the sun to us? Okay, so actually we have nothing, but the electron wave can propagate without any medium. Okay. And the properties, okay, we already discussed this part. These properties, let us try to become comfortable or complacent with that. Okay, because say the electron and proton attract each other, or the same type repel each other, and this is what we represent using the electric field, right? Electric field actually represents these forces, that you have force between electron and proton, or between protons you have repulsion. This is what the fields represent. But how do you explain why they attract? You all know, and you accepted it graciously without complaining anything. Okay, since your childhood, you accepted that electrons and proton attract each other. Yeah, you had no problem to accept that. Then you should also accept the fields. You don't ask why they attract, right? So you should also feel complacent with the existence of electric field. Okay, why they attract? Okay, I mean, if you have a proton, then another electron, if it is brought close to that, the electron will come to it will move towards the proton. Okay, so but there is space. While the proton didn't make a call, didn't call the electron that I am here. How come? How did the electron come to know that the proton is here? Okay, the proton didn't call him, and then then ask him to come close. So it's actually electric field, because electric field the electron understands. So this phenomenon is represented by the fields. Okay, so if you just take it in the way that Allah has made them like that, then you can easily feel comfortable. Allah has made them like that. With these properties Allah has created, so you can feel complacent. Okay, now the wave part. Well, wave refers to a variation, and we'll consider periodic variation. Okay, typically, I mean, you refer to periodic variation, and the parameter. I mean, the variation will occur in both time and space domains. Okay, so then you call it wave. Theoretically, okay, not theoretically, okay, also practically, the wave maintains some, I mean, basic features that they will be, but you know, I mean, these are just by definition, we have to mention them. Okay, they have to be single valued in both time and space. They have to be continuous in both time and space. Okay, the wave variation, I mean, you must not have any discontinuity, and it will be also differentiable in both. And I mean, the differential function is continuous. Then it is, if the wave function is continuous, then you fulfill the second condition. And if the differentiation of your wave function is continuous, then actually it is differentiable everywhere at all points of the wave. I mean, at all points, by all points, I mean at all values of t, at all values of space domain. Okay.
So what does single valued mean?
Single valued means, say, for all time instance, when you consider a wave function, say there is a wave, you have some wave existing, say from, say within our class period from 9:15 through 10:30. So if it is a wave, then at all moments, the wave has to have a value. Okay. I mean, there cannot be any discontinuity. As long as you have the value, it's a wave. Okay. Actually, we'll show you wave function. See, we are showing a wave function that at different time instants. Okay. Z here is the Z axis in the space. And we are considering one-dimensional wave for simple explanation. Now, the parameter, it can be for different things, but it is varying in the space domain. It could be temperature, it could be air pressure. Okay, so if it is air pressure, you have compression and depression, and that, I mean, you have a peak, means positive peak means you have the maximum compression there. So the air pressure is varying. In the space domain, it is varying, or temperature, or whatever. For us, we are considering fields. So the electric field, okay, is varying. Its amplitude, the magnitude of the electric field is varying. And at this position, you have the maximum value, amplitude of the electric field. Then the magnitude is dropping. But it is all happening in the space domain. I mean, consider some space. Okay, as you go in this z direction over this distance, you find a variation. And this variation you find at a particular time instant t1. Okay, time instant t1. So if you're standing still in time, at a particular moment, you find this variation. Now, as you move in time, okay, you will find that the variation that you had in the space will keep differing. Okay, the same type of variation in the space will not be retained. Okay, the variation pattern in the space keeps changing. And how does it change? As it, if it is a traveling wave, then it will change as if it is moving forward. Okay, like after a while, in another time instant or moment, T2, you find the variation looking like this in the bottom graph. So as if it has shifted towards the right direction. So if I could play, actually I'll show a video, but if I played video for this figure, then you could see that the wave pattern is moving forward. Okay? So this way electric field varies and also magnetic field varies, and there is a variation together. Typically, this variation take on this form. Give me a second. Okay, do you see something propagating?
Yes, sir.
Okay, so here the blue part represents electric field. The red one stands for magnetic field. So now you see, if I stop it, okay, at a particular moment, you find that the blue part, okay, has a variation. The magnitude of electric field is varying in the direction of propagation. Okay, the direction of propagation we are considering Z. So at a particular time instant, there is a variation for magnetic field and also for electric field and also for magnetic field, there is a variation. But if I go forward in time, this whole variation pattern keeps changing at the same space position. You don't, the same variation pattern is not retained. Okay, and how does it change? In the case of traveling wave, it keeps moving. Okay, so this is the example of traveling wave. Now, in this example, our electric field and magnetic fields are perpendicular to each other. Okay, and when they are like that, and also they are normal to the direction of propagation. See, the direction of propagation is Z, and Y is the direction for E, and x-axis is the direction for H. So they are all normal to each other. Okay. So this type of wave is called plane wave. Plane wave. Now this wave variation, if we want to express in function, okay, then we can use, say, the upper function, if function t minus z by vp. Okay, this sort of function we can use here for what we are showing here, that it is moving in the direction of positive z. Okay? But if we had a wave that travels in the opposite direction, in minus z direction, then the function would be like t plus z by vp. Okay. Now this function, I am using some generic function here, f1, f2, but this could be some sine wave. Okay, if it's just use one sine wave, then it represents one sinusoidal component. Say your whole wave may be non-sinusoidal, but you're splitting into Fourier components. So each of the Fourier components is a sinusoid. Okay, and that one sinusoidal variation you can use using a sine function here for f1. And that's the basic function we can use anywhere. Now, it may be surprising when it is propagating towards positive z direction. I have here minus, okay, in the parentheses, but if it is minus z direction, I have here positive. Why is it so? Okay, can you explain? When it's positive z direction, then I have minus side inside.
Because like sir, that negative counteracts the positive, so eventually একটা neutral চলে আসে.
Okay, by the way, what's your Christian number? I need to grade you a plus.
Okay, sir. Thank
Okay.
you, sir. It's 314, sir.
Okay, okay,
Yes,
but unfortunately I cannot do that.
yes,
I mean,
sir.
I just
I know, sir.
wanted
Yes,
to.
sir.
I
Yes,
wanted to, but I cannot.
no
Okay,
problem.
yeah. Well, you see that the function, okay, what does it do? It gives you, it returns you the value for certain values of your argument. Okay, I mean the argument can have variables or fixed I mean the constants, whatever. So for your argument, when you put the right values, it returns you the whole function value. Okay, the function always returns you a value for, I mean, you have to input the argument values, then it returns you values. Now, this function value, okay, say that represent, if it is, look at the top graph, okay. If that function value is like what we mark here using a dot, okay, this is at a position of z1. So this is the function value. Okay. So that we would get here when we put t1 in place of t and z1 in place of z. Then we get this function value. Okay, very good. Now, after a while, when you have the wave here, if we follow the same point, okay, it has moved a little bit, I mean, little bit forward, okay, a new position, which is Z2, and Z2 is higher than Z1. The value of Z2 is higher than Z1 because it has moved rightward, okay, in the positive Z direction. Now, at this moment, for this same position, the function definitely will return the same value. If we are tracking the same position, then the function value at this position, okay, we actually follow. So when we follow the same function value or the same position in the wave variation, then I should get the function should return the same value, but now for T2 and Z2. When you put T2 in place of T and Z2 in place of Z, you should get the same value. But if they are the same, okay, if these two values are the same, now you see T2 is definitely higher than T1 because in time you cannot go backward. After a while, okay, at a later time instant, we're considering here. T2 is, so if T2 is higher than T1, okay, then to keep this part constant, T2 of course has a coefficient positive, okay, and Z2 is also higher than Z1. So Z2 has a higher value than Z1, T2 has a higher value than T1, but to keep this constant, okay, well, I mean, this part has increased by the same amount. I have to reduce the second part, as he suggested, as 314 suggested, that to counteract, to nullify the increase in the first part. Okay, I have to reduce here. So Z2 has increased, but because of minus sign, it will drop. Okay, so you can get the same argument value that will return the same function value. So that's why when you have a wave moving in positive Z direction, you need a negative sign. Okay, so it can cancel out the increase in T. But when it moves in negative Z direction, Z will drop because, okay, the new Z will be lower than the old Z position. Okay, so Z will also drop. As you increase T, Z decreases. So you need actually positive sign to balance out. Well, now from here, I mean, if we equate the argument values, then we can find out an expression here, Z2 minus Z1, T2 minus T1. But that actually gives you the velocity of the traveling wave. A particular position is moving, and this movement has a velocity that we can measure, right? So say it has moved by a distance Z2 minus Z1, and over a time period T2 minus T1. So actually it is traveling at a velocity Z2 minus Z1 over T2 minus T1. So that is why, I mean, we have used a notation here, V. Okay, I mean, deliberately, the notation in this function wave function was set here V, because that actually indicates the wave velocity. Now it is called phase velocity because you know that we are considering a particular phase position within the whole cycle. Okay, periodic variation, particular phase. Okay, what does your phase mean? When you have a periodic variation, then every period you represent using an angular variation from 0 to twice pi. So different positions within your whole period you indicate using, say, 30 degrees, 60 degree, 80 degree. So these are then called phase positions, phase. Okay. So every point within the same period will repeat, and then you can again mark. So for any period, you can mark any position within the period itself, and that's your phase. So we are following actually a particular phase, say a particular phase. Okay, we were following here. So that phase is moving at this velocity. It is actually so it is called phase velocity. Now this sinusoidal function we can show using, you know, exponent, imaginary exponent. Of course, if you don't use j here, it is not a sinusoidal function. Okay, but using Euler's law, you know, I mean, sine theta from sine theta cos theta, you can also get exponent. Okay, but with j, but the exponent has to be imaginary. Okay. Now this t minus z by vp, this function actually we are showing here, omega t minus kz. Okay. For electric field, we show this way. If we consider plane wave, okay, is moving, we have one-dimensional variation, and we already defined what plane wave is. We have electric and magnetic field normal to each other, and they are also normal to the direction of propagation. Okay, and we can actually have equations for both electric and magnetic fields. Okay, now this is what we get for wave that propagates in the when you launch it in the air. Okay, so it that propagates free. So when it propagates free, it takes on this expression. Now, if we just equate with our basic form, in the basic form, we had this kind of equation, argument, right? So if you equate from here, then the VP or the phase velocity, okay, you get here this way. It will be omega by k. When you, to get it this way, you need to, divide here by omega so that the coefficient of t becomes 1. Okay? Then below z, you will get omega by k. So that's your VP. So omega by k represents your phase velocity. Now I need to say a little bit about k. Well, earlier we discussed that the electromagnetic wave can be basically of two forms, guided wave or a free wave. When you use an antenna to launch the electromagnetic wave in the air, the wave propagates free. Okay. And in this case, the coefficient you get here will be something k, will be something that is defined as k. And it solely depends on the, so actually is the case for plane wave, okay? When you have plane wave, then it solely depends on the medium properties, okay? And it takes on a expression like this k. Now, this part I am here just I just share. I'm just sharing here without any proof. But there is a course in microwave engineering in the 8th semester. There, that course I also offer, and there I show the proof here, proof for this for having a value of k for plane wave. Okay, so now please accept without the proof, and if you take that course, then you'll find the proof there. So now, for now, please accept that the coefficient of z here will be k, and you see that k has this value omega multiplied by root of epsilon and mu, where you have just three things. Omega has frequency, and then you have magnetic and electric properties, okay? Mu represented by mu and epsilon. So these are the basic properties of a medium. So it solely depends on the medium, how it will propagate. Now the velocity you get here by omega by k, and so you can cancel omega when you show k this way, and so you get VP completely material dependent. Okay, 1 over root mu epsilon. So you have only material properties there. So meaning that for plane wave, the electromagnetic, the velocity depends completely on the material property. Okay. Now, if it is free space, then we know that they will have mu naught and epsilon naught. And so VP will take on this value, which we call C. Okay. Now, in this course, for any wireless communication, please assume that we have plane wave in the wireless link. It's because when you launch the signal from the antenna in the close vicinity, it is not a plane wave. It is different. You have some complex form. But as you go a little further away, the wave becomes completely plane wave. And so, I mean, this small part will, in our next presentation, will show is actually very small. Okay, around the antenna and the transmitting antenna, you have a small region where the electromagnetic wave takes on some very complex form. But after that region, the electromagnetic wave takes on the form of plane wave, okay, which is showed using a video. So that kind of simple form, you have the electric field and magnetic fields. Uh, Both of them are normal to the direction of propagation. That's how it propagates up to the receiving antenna. Okay. So the light we have from the sun is a plane wave. Okay. And for plane wave, we have this expression. I mean, we have the value of k. But if we had a guided wave, okay, that you don't launch in the air for free propagation, rather you generate it in the circuit and the wave propagates through a guided medium, then it is actually not k here. Okay, you have something else. Okay, I mean that which is not only frequency dependent. It will not. It will depend on something else too. I
Sir,
mean, it will
would
depend
you
on how you.
kindly,
Yeah.
sir, would you kindly go to that slide, sir, the one before this? Yes, sir. So here, sir, you are showing that in terms of electric field, the quantity E and E naught are vectors. But for plane waves and magnetic field, are they vectors or are they
No,
scalars?
they are vectors. They are
Okay.
vectors. We are just
Okay.
considering their magnitudes.
Okay.
Okay. For plane wave, we have. Uh, I mean, we have a single direction for our electric field or magnetic field, right? I mean,
Okay.
uh, in the y-axis we showed the electric field. In the x-axis we have magnetic field. We have simple. I mean, in terms of direction. Okay. So that's why we have here simple expressions. Okay. Any other questions? Okay,
No, sir. No question.
now please make an assumption for any problems in the exam which don't specify otherwise. The assumption is that you please, I mean, it is a plane wave. Okay, whenever I consider any wireless link, you consider the electromagnetic wave to be a plane wave. Also, you consider the space to be free air or free space. Okay, the medium, uh, you need to consider air or free space, meaning that you already have the velocity of your wave. Okay. Now, it may happen that for the calculation of something in the problem, you need the velocity of the wave. And I'm not giving that in the question, but that you actually already have. Got it? So since, I mean, if you find that I don't mention anything specific, that you have this kind of medium or this the form of wave, then you consider plane wave, you consider free space or air. So you consider that you have k, okay? The coefficient of z is k. You have this expression for k, for the coefficient of z. You also consider the velocity to be like this, okay? But I suggest you to use this round figure, okay? I mean, you'll still get marks if you use 2.98, okay, the detail, the accurate figure. But if you use this round figure, that will make my life easy when I grade your script, okay? Well, it's almost 10:30. Any questions?
No, sir.
Okay, so we'll go from here the next day,
Okay.
and bye until then.
Okay. Assalamualaikum, sir.
And
Sir, what
alaikum
about the
salam.
attendance, sir?
Oh man,
Yes, sir.
I forget every day. Okay.
but we have a class right now, sir.
Yeah,
We have to
yeah.
leave,
So
sir. Yes.
today everybody I'll consider present, but tomorrow please remind me.
Oh, thank you, sir. Assalamu alaikum.
Jazakallah. Alaikum assalam.
So much.
Alaikum assalam.